Yo, what's up everyone? Welcome to the 2022 USNCO local exam thermodynamics section. This is going to be from questions 19 through 24. So let's get started with question 19. A container with 100 grams of ice at 0 degrees Celsius is placed in a humid room whose temperature is 40 degrees Celsius. The ice melts as water vapor condenses into the container. Assuming that all the heat transferred to the container comes from condensation, how much water will have condensed into the container once all the ice is melted and has reached 40 degrees Celsius? And we're told that the heat of fusion of ice is 334 joules per gram, and the heat of vaporization of water is 2,260 joules per gram. All right, so let's understand what's going on. We have a container that is 100 grams of water at 0 degrees Celsius, and it basically just turns into liquid water. It goes from 0 degrees Celsius to 40 degrees Celsius, and that's still at 100 grams. So the system is gaining energy from the surroundings in the form of heat. Since there's a temperature difference between the system and the surroundings, you have a heat transfer. In this case, we know that we took 100 grams of water up 40 degrees. So there's going to be an energy change. There's going to be a heat associated with taking the temperature up. And that energy is going to be in the form of Q equals mc delta T. The energy, the heat, is equal to mass times specific heat capacity times temperature. So one of the energies that is introduced into the system is the energy required to raise it 40 degrees. So we have 100 grams. And we know that the specific heat capacity of water is 4.18 joules per gram times Celsius. Times the change in temperature is 40 degrees Celsius. So Q comes out to 16,720 joules. So that's one of the energies associated with this change here. There's another energy associated with it, and it's the energy required to take the solid water and liquefy it. That energy is the fusion of ice. The fusion of ice tells us that whenever you have ice and you take it to liquid form, you're going to need 334 joules of energy per 1 gram of ice. So there's going to be another energy associated with the fact that we took 100 grams of ice to water. So we know that it's going to be 334 joules per gram times the 100 grams that we have. So that's 33400. That's the other energy that's been introduced into the system. So let's sum up our energies. So we have 16,720 joules plus 33,400 joules, and this comes out to 50,120 joules. Now, why did we calculate this value? This value represents all the energy that the system has gained. And in order for the system to gain that energy, the surroundings must lose that energy. The way the surroundings is losing that energy is by having condensation happen. So when condensation happens, our heat of vaporization tells us that for every 1 gram of liquid water, for every 1 gram of gas that we have, if you take it into its liquid form, it's going to release 2,260 joules of energy. So if we have 50,120 joules of total energy, if we divide that by our heat of vaporization, we should get the amount of water that has condensed onto this container. So 50,120 joules divided by 2,260 joules per gram, and that is going to give you your answer, which is about 22.2 grams. And that is answer choice C. And that's how you do question 19. Let's go to question 20. The standard enthalpy of formation of hematite F2O3 is negative 825.5 kilojoules per mole. What is the standard enthalpy of reaction for the reduction of hematite with carbon monoxide to give metallic iron as shown below? So we're technically given two reactions. We're given the enthalpy of formation reaction, and we're also given this reaction here. we have to use these two reactions that were given and manipulate them in order to get this final reaction that we have here. Once we've done that, we can add up all the enthalpy values using Hess's law to find the enthalpy change associated with that bottom reaction. So we said that we had two reactions. Let's just write them. It's carbon monoxide gas reacting with 1/2 moles of oxygen gas to give carbon dioxide gas. And this has a delta H of negative 283 kilojoules per mole. All right. The other reaction that we have is going to be the reaction of the formation of hematite. So we know that our enthalpy of formation deals with the reaction where you form one molecule of your product. And one molecule of our product is F2O3, and this needs to be made up of iron atoms and oxygen atoms. So these are O2 atoms, and we need a coefficient of 2 and a coefficient of 3/2 to balance these out. We know that this reaction has a delta H of negative 825.5 kilojoules per mole. And we're told this from our problem statement here. So how do we take these two reactions and get the bottom reaction? You can find this out using trial and error, but basically the combination of these two reactions that yield our final reaction, it occurs when we take 3 times our first reaction and the negated version of our bottom reaction. So let's write that down. We have to take 3 times our first reaction, so 3CO with 3/2 O2, yielding 3CO2. And the enthalpy change associated with that is just going to be negative 283 kilojoules per mole times 3. And this is just because we multiplied the whole thing by 3. And so the other reaction, we need to take the negated version of it. So the negated version would have the hematite being a reactant, and it's yielding 2 iron atoms and 3/2 of this oxygen molecule. And the enthalpy change associated with this would just be the negated value of the value we have right now. So we would have 825.5 kilojoules per mole. And so if you like kind of crossed out everything and got your final reaction, you'd realize that it's Fe2O3 reacting with 3 carbon monoxide to yield 2 iron atoms and 3 carbon dioxide atoms, which is the exact reaction that we want. And so all that there's left to do is work out the math. So with Hess's law, the enthalpy change associated with this reaction would just be the sum of the enthalpy changes of these two reactions. So the enthalpy change would be negative 283 times 3 plus 825.5, and all this would just be in the units of kilojoules per mole. And this here comes out to negative 23.5 kilojoules per mole. So the enthalpy change associated with the reaction that we want is negative 23.5 kilojoules per mole. And if you look at your answer choices, that is answer choice A. So the answer for question 20 is A. Let's go to question 21. Which of the following equations correctly describes the change in internal energy, delta E, of a reaction taking place in a bomb calorimeter? And we have two equations here. Now remember, in a bomb calorimeter, you're going to be keeping pressure constant. And one of the definitions of our change in internal energy was that when pressure stays constant, our change in internal energy is just the heat. And so the first reaction makes sense. It's a definition. Under constant pressure, which is what we have, this is true. And the second one is a variation of your enthalpy enthalpy formula. The official definition of our enthalpy was, or at least change in enthalpy was, the enthalpy is equal to the change in internal energy plus volume times the change in pressure. This tells you that your change in enthalpy is the change in internal energy and the change in the energy it takes for that system to exist. So enthalpy is all the energy associated with a system, and that includes all the internal energy of a system and the energy required for that system to exist in space. And so you can just rearrange this equation to get our second equation. And since our top equation was a definition equation, then any variation of that would make sense. So 2 also does make sense. Therefore, our answer is C. Let's go to question 22. Cyclopropane isomerizes exothermically to propene as shown. The carbon-carbon single bond in propene has an estimated bond dissociation enthalpy of 345 kilojoules per mole, while the carbon-carbon double bond in propene has a bond dissociation energy of 611 kilojoules per mole. Assuming that the CH bonds in propene and cyclopropene all have the same bond dissociation enthalpies, what is the estimated bond dissociation enthalpy of a carbon-carbon single bond? So there's a lot here, but the main thing to know is that our change in enthalpy is going to be the bond dissociation enthalpies of the bonds broken plus the bond dissociation enthalpies of the bonds formed. Remember, when bonds are broken, energy is taken in by the system. So this is going to come out to a positive value, but when you form a bond, the system actually loses energy. So this ends up becoming a negative value. All right. So we know that cyclopropene going to propene is going to be have a change in enthalpy of negative 32 kilojoules per mole. So one of the sides of our equation is already done. We know our change in enthalpy is negative 32 kilojoules per mole. And so now let's look at the bond dissociation enthalpies of the bonds broken. Now, in this reaction here, the bonds that are broken are all the bonds in the cyclopropane. In the cyclopropane, you have 3 carbon-carbon single bonds, and you have 6 carbon-hydrogen bonds. So you have 3 times whatever your carbon-carbon is for cyclopropane. You also have 6 of your carbon-hydrogen bonds, and that is the bond dissociation enthalpies of the bonds broken. Let's look at the bonds formed. So we know that since we're forming the bond, we're going to need to negate all these values. So what are the bonds being formed in propane? Well, you have 1 carbon-carbon bond, and remember, the carbon-carbon bond doesn't necessarily have the same energies in both the cyclopropane and the propane. So let me just put a subscript here of I guess another C to represent that this is the carbon-carbon bond dissociation enthalpy in cyclopropene. And so we have 1 of our carbon-carbon of propene. But remember, since this is being formed, let's just put a negative to negate everything. Another thing here is a carbon-carbon double bond. So -1 times our carbon-carbon double bond. And you also have 6 carbon-hydrogen bonds here. So -6 carbon-hydrogen. Okay, there's a lot here, but there's something that we can do to clean up this equation that we have here. We have 6 of our carbon-hydrogen bonds here, and we have -6 of our carbon-hydrogen bonds here. And we can cancel them out because we're told that the CH bonds in propene and cyclopropane have the same bond dissociation enthalpies. So what we're left with is that -32 kilojoules per mole is equal to 3 times your carbon-carbon bond dissociation enthalpy in cyclopropene, which is, by the way, what we're trying to find. So that's CCI, and you have plus and then all this minus expression. We know our bond dissociation enthalpy of our carbon-carbon bond in propene. So that's -1 times 345 kilojoules per mole, and that's from this part of our problem here. And so now we need to find out our carbon-carbon double bond, and we're also told that it's 611 kilojoules per mole. So let's do -1 times 611 kilojoules per mole. And so all of this is equal to -32 kilojoules per mole. And all that there's left to do here is solve for our carbon-carbon bond dissociation enthalpy in our cyclopropane that we have here. So you just do a bit of algebra to find out what that carbon-carbon in cyclopropane is. This number comes out to 308 kilojoules per mole. And if you look at your answer choices, that is answer choice A. So the answer for question 22 is A. Let's go to question 23. Two reactions have similar change in enthalpy values, but reaction 1 has a much smaller standard entropy change than reaction 2. At 298 Kelvin, what statements about these two reactions must be correct? So statement 1 is that reaction 1 must have a larger equilibrium constant, and statement 2 is that reaction 1 must have a larger Arrhenius prefactor. The one I want to go over first is number 2. An Arrhenius prefactor is something in kinetics. So when reactant molecules collide, there's a certain probability that they become products. Not all collisions between reactants result in products occurring. Your Arrhenius prefactor is the likelihood of your reactants turning into products when they collide. Now, the problem with this is that we're talking about thermodynamics here, and we're trying to compare it to kinetics. We have thermodynamic ideas like entropy and enthalpy, and we're trying to connect it to kinetics. And you just really can't do that. There's not really much of a connection between thermodynamics and kinetics. So 2 is just an assumption we cannot make. 2 is wrong. So let's look at 1. Reaction 1 must have a larger equilibrium constant. Now, we're going to disprove this using 2 of our equations here. One of the equations that we're going to use is that our delta G is equal to delta H minus T delta S. Our change in Gibbs free energy is equal to our change in entropy minus T times our change in entropy. The other equation that we're going to use is the fact that delta G is equal to minus RT natural log of K. Now, this equation in this form isn't that helpful, but if you isolate K comes out to e to the negative delta G over RT. Now, as your delta G gets bigger, if you look at our K expression here, our K equation, as your delta G gets bigger, that exponent gets more and more negative. When that exponent gets more and more negative, your K ends up going down. So as your delta G increases, as you have an increase in delta G, that's equal to a lowering of your K value. That's a lowering of your equilibrium constant. So greater Gibbs free energy values means lower K values. Now let's tie that back to our first equation here. We know that our delta G is equal to delta S minus T times delta G is equal to delta H minus T delta S. If the two reactions have similar delta H values, all we have to look at is this T delta S value to find out which one is going to have a larger or smaller delta G value. If reaction 2 has a much greater entropy value, change in entropy value, it means that our reaction 2, the delta G of reaction 2, is going to be smaller than the delta G of our reaction 1. Using this equation, we already proved that as your delta G value goes up, your K value goes down. So that means that if reaction 1 has a greater delta G value, it's going to have a lower K value. So the K of reaction 2 is going to be greater than the K of reaction 1. And that is the opposite of what we have in, choice 1 or whatever. So choice 1 is wrong, choice 2 is wrong. Therefore, our answer is D. Sorry about that. Our answer is D. All right, so the answer for number 23 is D. Let's go to the last question, which is question 24. Which reaction has a change in entropy of greater than 0? And we're told that all our reactants and products are liquids. The fact that all our reactants and products are liquids means that we can't really depend on phase changes to dramatically change our entropy. All right, right away there's two answer choices that don't make sense, and those answer choices are A and D. We know that as you increase the number of molecules that you're dealing with, your entropy goes up. So if we went from 2 molecules to 1 molecule in answer choice A, that would be associated with a lowering of your entropy. And it's the same thing for answer choice D. Going from 2 molecules to 1 molecule is going to lead to a negative delta S value. All right, so now we're left with B and C. The thing you need to know for B and C is that open chain molecules have greater entropy values than closed chain molecules. Open chain molecules have straight chain open chain molecules have greater rotational. I guess they have the ability to rotate. Whenever you're in a cyclic form, the bonds are really tight together and they can't really move. What that means is that your entropy is much lower in cyclic systems. So the fact that you're going from a cyclic to a straight chain molecule in answer choice B means that you are increasing your entropy. The fact that you're going from something open to something cyclic means that you're lowering your entropy. That means that C is not the right answer, and therefore B is the right answer. So the answer for number 24 is B. And that's all I have. I hope this was helpful. I hope you were able to learn something, and I hope to see you later. Thank you.